Devlog, 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 Devlog. With the ritual complete, we can begin the devlog. In the last part, I worked on a physics calculation for calculating rope physics in Unity without the use of rigid bodies or any physics actual calculations, purely with mathematics. And in this part, I work on the actual implementation of why I added ropes to the game and using those in the game now. I'm making grappling hooks in case that wasn't especially clear. So let's point out what I first want to achieve with this system, what I want to have happen in this system, and I will explain all of these design choices later. What I want to achieve with this system is to be able to fire a left grappling hook from your left side with the left trigger and a right grappling hook from your right side with your right trigger. These grappling hooks will then find areas in the game to logically hit onto. They will then pull the character, based on a mathematical calculation of tension, towards those points based on how tense this rope is, in relativity to the other rope and in relativity to the player's movement direction and velocity. This rope system will work on a substate system, which means it will work on top of our grounded, in-air, water system states, wall running states, and other state systems, based on how we interact with the game space when we are using our grappling hook. Does any of that make sense? I hope not, because I haven't explained it yet. The first thing I did was fix a glitch with the rope system. This glitch is when going past very small objects, our rope will occasionally clip through the object. The way this is working is that we have our tension point on this small object, and then as we run past it, we can see past this object against the corner of our rope to our previous point, which means from our logic system setup on our ropes, we can detach the newest point of our rope. This is just a logic-based glitch, but it's interesting how it came about. So, since this system works with the collision setups of our in-game objects that we are tangling our ropes around, this only comes up if we are running against a small object and an object that is not very detailed and an object that has a parallel line to the previous object. All of these have... I forgot my word. I'm just flapping my hands around until I can think of what I was saying. All of these systems, when put together, result in this glitch. So, essentially, if you've got track of what I just said, this means that this glitch only comes about when we have a bunch of fin-based cubes set up without any rotation added to them. This glitch only came about because I was really lazy when I was setting up the debug testing area. Because of this glitch isn't actually going to come up in gameplay, but just to be safe, I did fix it. The way I fix this is when we have a tension point, we will then have lerp tension points between our previous tension point and our current tension point, very close to our current tension point. These add additional tension points on our rope that are invisible to the viewer, but visible to me through the code. Then we have these points and we have to check through these before we can check through to our previous point. This means we'll have to check through all of these smaller points around tension points, which would then make more collision points the player has to see before they can detach this collision point of the rope. These won't come up unless you can more clearly see this point of the rope, and therefore we will not detach our rope from smaller objects. This doesn't have any issue on larger object collision because we can easily detach our rope from these collision points when we can see them, so this only comes up on smaller collision points on surfaces. I kind of zoomed through that section because it wasn't very interesting to me. It wasn't a huge fix, but I just wanted to point out that that is fixed. I then had to calculate the tension for each of our ropes. This is essentially how much this rope is going to be pulling our player back. This is calculated by the length of the rope, the amount of points in the rope's tension, as in how many points they have curled around, the angles of these points, as in how complicated and different are the points that we have curled around, the distance to the closest point to the tether, and the distance overall of the tether being the rope. I accidentally used the words rope, tether, and grapple interchangeably throughout this devlog and my coding. When I use any of these words, I mean the rope. Just to clarify. The way our tension works is this returns a value from 0 to 1, 0 being there is no tension on this rope, which will never happen, 1 being there is the maximum amount of tension on this rope. This is then fed or read by the, well, I guess not read. The movement script searches for this, so I guess it's collected and then read, but this is collected by our movement script and is used to calculate things like speed, velocity, and angular movement towards our ropes. I'm just gonna fully explain over the mathematical calculation for this one because it was really fun to do, even if it is very mathematical. So what I do is I run a distance between all of our rope tension points, how close they are to the previous tension point. This gets the maximum distance of our rope. This one's pretty easy, just tension points. I will then add up the difference of angles between the previous 5 of our rope tension points. The reason I picked 5 is because usually tension points of ropes can have upwards of maybe 60 or so angles, and checking the angle difference between each of these points against the previous points just takes a whole lot for the scripting to do for twice per rope. So not twice per rope, twice per player. The player has 2 ropes. Twice per player. It takes up a lot of time, so I just neglected this point, and I will explain why in a moment. Once you've run through the script, we'll have our full length of our rope, we'll have our angle of the previous points of our ropes. We will then find the distance between our closest rope from our current position, so this is how close we are to our last rope, and then we will find the number of tether points altogether. So we have 4 of these different angles, or float values. We'll have 4 different values. Each of these values have a different priority for how much tension they will apply. The least amount of tension is the angle difference. This is just not a very important part of this. It's only mildly going to add tension to our rope, so the way we do this is we multiply this value by 0.25 and then we square root this value. This gives us our angle tension value. We will then find out the closest distance value. We've already had this, but all we do is we times this by 3, and then we times it by 3 plus the amount of point tensions we have. So essentially we're timesing our distance to our closest rope by a multiplier of 3 plus n being the amount of points we have. So if this was 12 points, we would have this multiplied by 15. This increases a very large number, and we'll get onto why it needs to be so large in a moment. This has a priority of 1, meaning it's more prioritized than our angle value, but less prioritized than the next 2 values. The next value we have is the number of tension points we have. This is how many things we have curled around. This has a priority of 2. It's going to add a lot of tension if we have wrapped our rope or our tether or our grapple or what have you around a lot of points. This value is our tension points multiplied by 3 and then square rooted. I like using square roots a lot. They make me feel clever. And the next value is our full distance of our ropes. This is going to be a very large value. It has a priority of 3. It is our most prioritized value, and it will have the most amount of tension calculated within it. We don't really do anything with this value because our distance of our rope fully is going to be a whole lot more than any of our other values. Except for our closest distance, only if we have a small closest distance. Once we have these values, we find the value of A. A is our point tension, this being the amount of tension points we have overall, which was our square root of our tension points, if you remember, multiplied by our angle tension, not multiplied, added onto our angle tension and our point tension added together. Then we find the value of B. B is the square root of our... This is going to get complicated. I realize as I'm reading this that I may have gone a bit overboard in the complicated mathematics. Oops. This value is value B being the closest distance of our tether. This is our distance to our closest tether, the value we just made before, multiplied by A, plus our overall distance multiplied by A, and then the square root of this value altogether. We will then find a value of 0 to 1 based on this value divided by 100. This value just That's a kind of arbitrary number to divide by. The reason is that it's just not going to get to 100 based on my coding of how long these tethers should be, but don't worry about it. This returns a value of 0.221, but this value is then fed into our player scripting, which can also multiply this by a value. So if I want this to be less intense, I can just multiply by 0.5, or if I want this to be more intense, I can multiply by 2. It doesn't really matter too much. It just returns a value between 0 and 1. The reason I'm square rooting things so much is because at higher numbers, it's just not going to have as much returns as lower numbers. I wanted this sort of feeling of diminishing returns, so the ropes have more tension added to them at smaller distances, and then at larger distances we're already reaching our maximum tension points, so we're not going to be getting exponentially higher. There's a reason for this, which I will get onto when I talk about the movement system. But essentially, to summarize the reason of this very easily, is I don't want to have extreme number values for speed being returned. So I'm sort of clamping down on how extreme the tension and tethers can get by square rooting things. The next thing I did was work on the rope targeting, and this is surprisingly complicated. I put out a YouTube poll, one of those things that you can respond to and click on the inputs to give feedback. I put out a YouTube poll of what people thought was the best way to have target acquisition when using a rope swinging system, because I genuinely wasn't sure. The three options was based on your forward position of the player, this being the direction you're facing, based on your input direction, this being the direction on the input pads that you pressed, and then based on the mouse look direction, as in what the camera is looking at. It was resoundingly feedbacked to me that the camera look at direction was probably the best option. I then completely disregarded this feedback and made it with the input direction. Why did I do this, you ask? Well, because aiming with the camera would be disorienting, I felt. Essentially, this game never uses camera look direction to accommodate for any of the movements because it's not a shooter game. Those use camera direction a lot to use your aiming. In a shooter game, you're already used to using the camera as an input to direct what you're aiming at, but in my game it's more platformer based, and if I do have combat it's going to be more action based, so nothing really relies on the camera's viewpoints. So if I make an equipment setup that uses the camera's viewpoint, it will be disorienting for players to go from not using the camera's aim to all of a sudden using the camera's aim. Furthermore, which is a connective word I used a lot in high school during English class to do my writing. Furthermore, if you're moving really fast with the grappling hook, it's going to be really difficult to aim with the mouse button because you're going to have to swing the camera around really quickly, and it's just going to be kind of awkward to do. So what I did was I made it so that the player aims with their input direction. However, this has the new issue of when the player is aiming, they have to actually be able to organically hit things that they would want to hit. So the player's input direction for aiming the grappling hooks has to be adaptable and easy enough to use so that they could hit anything that they would reasonably want with just a simple button press. This means that the grappling hook system has to be incredibly forgiving with aiming, and if you ask me, that's just a given for grappling hook systems in general. They don't require pinpoint accuracy, just are you pressing in the vague direction of something? Cool, you did it. You made a hit. So, this means I have 4 different options for aiming. We are either, well, I guess technically 5, but the 5th one is the first one. I'll get on to that. The first one is we are pressing forward of the player. This is we are pressing an input within 45 degrees angle of the player's forward direction or the player's movement direction. They're pretty much the same thing. If we're doing this, we will have free aim to go anywhere we want in this input direction, and input direction will not be altered in any way. The second option is we are firing from the side that our grappling hook is on. Remember, we have a grappling hook on our left side and a grappling hook on our right side. So if we're pressing right, this would be our grappling hook's right direction firing. In this instance, if we're pressing the side that our grappling hook is corresponding to, we will have free aim as well. The third option is the side that the grappling hook is not corresponding to. So this would be if we have our grappling hook on our right side, we press left, we activate our right grappling hook, and then we have a grappling hook fire based on that situation. In this situation, we shoot from a upwards diagonal direction. So if we are using our left grappling hook, we press left trigger, but we are holding right. We are trying to aim rightwards with this. We will then aim from between our forwards direction of our character, or our forwards inputs direction, what would that correspond to? 45 degrees to the right. So this is as far right as this grappling hook can aim. Finally, we have backwards aiming. This is the character aiming backwards. This is the exact same as the opposite right direction, only we have the backwards version. Essentially, we have free reign of firing backwards unless we cross the point of firing backwards and then towards the opposite direction. So if we are firing from our left grappling hook again and we press backwards, we can fire backwards. If we are using our left grappling hook and we fire backwards and to the right, we are limited to only firing backwards. We can't cross that boundary to fire backwards and to the right. So this is our input direction. Now I have to go over the actual aiming. The aiming direction has 3 overrides, this being how far, how our distance is for our aiming. No, it has 2 overrides. It has 2 overrides, ignore me. This is how far we are aiming, this is how the distance we are traveling, so this is usually between 25 and 30 units. There's not a huge difference. Essentially, if we are traveling faster, we have a bit more aiming direction because we're going to be trying to aiming for things further ahead because we are going quicker. And then we have how far upwards we're going to aim. If we are standing perfectly still, or not moving at all, or moving at very low speeds, this will be further upwards because we are trying to gain upwards verticality with our grappling hooks. But if we are moving quickly, this will be further forwards because we're already using our grappling hooks to move very quickly, or we are already running very quickly, so we're wanting to use our grappling hooks to build more speed, so we should be aiming for things in front of us to grapple around, to build speed and pull us forwards. So in this instance, we're going to aim more closer to the ground, but still pretty far up. I'll explain that in a moment. And in the first instance, we're going to aim further up. Finally, we have our actual grappling hook aiming. This is, I was surprised this part took so long to record the simplicity of aiming, but what we do for this section is we just have a variety of sphere casts. These are like chunky rays. These go from, depending on the ray, either left to right or right to left. So the right ray, for example, will go, if we're aiming forward, it will go forward. If we don't make a hit, it will try forwards and then further to the right and then further to the right and then further to the right, sort of in an arcing direction. I mean, I'm hoping I'm showing the video version of what this looks like and you're not just going on my audio, because that would be really confusing. I really hope I didn't edit the video in that way. And then if we don't have any of these hits from going further right, we will try the same, but we'll go further downwards. So if we didn't make any hits at the top of where our ray is aiming, we will go further downwards, and then we will go 1 step downwards, 1 step to the right again, or to our direction again, and then 1 step to the right again until we reach the end of our arc. Then we'll go a step downwards, and this will carry on for the approximation of however many rays this system is using. I think usually around, I don't know, 40? 50? Who's to say? Essentially, the system uses a lot of sphere casts just to make sure that we are actually checking. There's a wide berth of things that we could be aiming at. So this just wants to accurately check in a general area. I could use the same method with just using one sphere cast, of just making a gigantic sphere cast in one direction, but the issue with this is it could have error hits if it's a sphere cast of aiming on the walls of something or not going through small gaps to aim or things of that nature. So personally for my working, I would rather use a array of more detailed sphere casts instead of one larger one, just because I would rather have more details if it's to do with aiming and target acquisition. If we have made a hit, all we do is check from this point back to the player, but with all collisions. So this is not ignoring any collision, and this is anything that could interfere with our grappling hook, because we can only grappling hook onto certain certain layers. So this is just from what we hit backwards, just to check for any extra collision. There usually isn't any, and if there isn't any, we will return that this thing can be grappled onto. And that's the simplicity of target acquisition with a grappling hook. Wasn't that easy to explain? Next we handle the rope's rotation and how it should rotate the player. This is a section I completely forgot to record because it was so pointlessly uninteresting. This is essentially calculating what the player's forward direction should be relative to the ropes. If we have one rope that we are grappled onto, we will attempt to rotate towards our position to that rope, rotated by 90 degrees, either clockwise or anti-clockwise, depending on what the rope is. So for example, if it is our right rope, it is our position to the right rope, rotated 90 degrees anti-clockwise, so that the rope is at our right side of our player. This is pretty easy to do. We just use a quaternion calculation on our vector free direction from our player to our rope, multiplied by 90 degrees. Very simple. Then if we have two ropes, we run these calculations for both ropes, and then we find the normalized direction that they should face to. This direction is probably always going to be the same direction, but I just run it on both ropes just to be safe. But realistically, if we have two ropes fired, the direction from the left rope that we should rotate to and the direction from the right rope we should rotate to should be pretty much identical, so no real issue. Then depending on our control, if we are on the ground or in the air, we will have a certain amount of control set to rotate towards these systems and a certain rotation speed for these systems of our rope system. You know, usually in these devlogs for new movement systems, the recast targeting and collision setups are usually the easiest part, and the actual coding of the physics, air quote physics, there's no actual physics, I have to point that out every single time, otherwise I am cursed indefinitely. The use of these movement options on top of your regular movement options or coding how they should move is usually the more difficult aspect, and it has been the complete opposite for this system somehow. Actually coding this in terms of movements is just easy. So here's what I do for adding this rope tension to our movement system. It's very simple. All I do is I calculate from our rope tension value that we calculated earlier. Remember that part of the devlog 20 minutes ago? We use our tension value that we have found earlier. We find a direction from our current position towards the last point of the current rope that we are checking. We check from our left rope and then we check our right rope. Then they're added together, don't worry about it. We check in this direction, we then find a value for our tension on our rope, and we find a value for our length of our rope. This is run through the tension calculator I mentioned earlier. We will then use a free value lerp to calculate how much speed should be added. This is a value from our rope's minimum speed, our rope's mid speed, and our rope's maximum speed. If you don't know what a free value lerp is, a lerp is usually using two values, 0 being one value, 1 being another value. All we do is we have our lerp. If it's less than 0.5, we use a lerp multiplying this value by 2 and using 0 to whatever our 0.5 value is, and if it's more than 0.5 value, we use a lerp of this value minus 0.5 multiplied by 2, and we use our mid value to our max value. That's just a 3-point lerp. If you haven't really used those before. They're pretty useful for having oddly shaped lerp functions. The reason I did this this way instead of just a single 2-value lerp is I want there to be a large amount of difference between our rope's minimum speed and our rope's mid speed, as in we're not moving very quickly and we're moving 0.5 towards the rope very quickly, and I want it to be a very small amount of difference between our rope's 0.5 speed and our rope's 1 speed, this being the maximum amount of tension and the mid amount of tension we can have. This is because I don't want there to be an extreme amount of speed added if we're going at our maximum amount of tension, because usually in this system, what would happen is that in these very, very difficult to achieve extreme values, you would have to be moving at so fast of a value to make the minimum or midpoints of the lerp have a natural feeling amount of speed, that the final value would have to be so exponentially higher compared to the first value. So with this system of a 3-point lerp, the mid value can be something reasonable, and the max value isn't something exponentially big. Then if our rope has reached its maximum length, this being the maximum amount this rope can be, this is just how much is tangled around things, we'll add a break amount to our speed and then clamp this at a higher value. Essentially what this means is if we are going really far with this rope, we need to be pulled back to make it to the actual length of this rope should be. So at higher tensions, this is going to be adding to our already tense rope to pull us back even further, because we are reaching way too high on this rope's distance. And at low speeds, at low tension, which really, now that I'm thinking about it, will never come up as far as rope tension goes, because if we're reaching the maximum amount of length of this rope, we're already building a huge amount of tension, but whatever, we're breaking even further and we're being pulled back. So we're ignoring how slow we would be moving. I just realized that I've been playing with a fidget toy this entire devlog, and it makes a loud clicking sound, so I'm not re-recording this, so sorry about that, about the weird clicking. That was me. That was little old me playing with a toy. Finally, we have a vector-free value, which is our direction towards the rope. We multiply this by our speed value we have gained. We add this to our overall rope tension that we are building, and we also add our tension amount to our overall tension. This is just a value that is how tense our left rope is and how tense our right rope is. More on this later. We'll run the same value for our right rope, so this is our left rope and then our right rope. We will add the tension of our right rope to our overall tension, and then if our left rope is active, we will add our overall tension plus our right rope's tension divided by 2. This is just so it has a value between 0 and 1 still, and if not, we will just add our overall tension of our right rope to our overall tension and not divide by 2. This is because there isn't already a value, so we don't need to average it out to a 0 to 1 value. Then the next part is pretty simple. We already have our direction that we want our player to move based on their inputs. This is the player's input direction relative to the ground, multiplied by our player's speed, and all we do is we add our rope velocity to this amount. Pretty easy, pretty simple, pretty easy, and also simple. Like I have mentioned in the past, this is a substate system, so it's deriving its logic primarily from our base system of our grounded movements. So all we need to do is we're using this as an override to plug in different values to our movements. So all we're doing essentially is we're calculating how tense our ropes are, how much they're going to move the player, how much they're going to rotate the player, how much speed they're going to gain to the player, how much speed they're going to lose to the player. We're plugging these values into our already existing player movement values, and then the scripting works exactly the same as normally. There's no additional movement scripting adding, it's just calculations for how much velocity or how much speed the player should have. This is the beauty of substate systems. It means that whenever I need to make a new movement ability, I can just do it like this, super easily. Next we have the ropes transitioned into the in-air system. This is when the rope is pulling you into the air. It doesn't do this immediately, except for when it does. If the rope is so far above our character that they are going to be immediately pulled into the air, we will just launch them into the air initially. If they are not, and they are applying upwards tension above a certain amount, this will build up over time as the player is on the ground, and then eventually they will be pulled into the air. Furthermore, if the player is running downhill while having a rope that is pulling them uphill, they will be launched into the air as they are going downhill because they are trying to go further down, or they're trying to go off a step or something like that. I don't know, just an example, I don't know. While also being pulled harshly towards the air by their rope. So in these instances, the player will also just be pulled into the air from their rope that is pulling them into the air. I haven't actually tested this part of the system, so I don't know if it works well movement-wise, but it just seemed what would logically be in place. For example, if you were to try and run down a hill while you're already being pulled up in the air by your rope and you're barely just not being launched off the ground, if you're trying to go even further downwards, you're going to be pulled off the ground even harsher by the rope, and it should just launch you organically into the air. Next, we have the way the player builds speed when using a grappling hook. This is primarily a system that is used when the player is on the ground and using a grappling hook, because when in air and using a grappling hook, we're not really going to build as much speed because we're not running on the floor, but we are still going to build speed, so I probably shouldn't have mentioned that in the first place because it confuses the point. Essentially, when the player is running towards their grappling point, as in the velocity that they are being pulled towards with the rope, they will build speed as they are moving towards it, and when the player is moving away from it, they will lose speed. This is aside from the velocity added to our character. This is an independent value that is affecting our character's current speed. The value you see in the top left that says current speed equals 7.6. This is a really simple function. If the player is running towards the grappling hook tension velocity direction at a value of above 90, as in they are running towards it above a 90-degree angle, they will build speed. So this means that we can actually run parallel to this rope and still build speed. We build speed relative to the tension of this rope, as in how much this rope is pulling against us. If it's a tighter rope, we're going to be pulled towards it faster, meaning we're going to build more speed. If it's a looser rope, we're going to build less speed. Furthermore, depending on how we are running towards the rope, depends on how much speed we're going to build. If we're running straight towards the rope's velocity direction, we're going to be building a lot more speed compared to if we are running parallel to it at a 90-degree angle. We then run the reverse function for if we are running away from a rope. If we are running away from a rope at a harsher angle, we will lose speed faster, and we will also accelerate to these points faster, depending on if we are closer in our movements towards the rope than if we aren't close to the rope. Essentially, if we run towards the direction of the rope's velocity, we're going to be building speed. If we run away from it, we're going to be losing speed. This is all pretty obvious. I then made this new running animation. This is the running animation that will play when we're going very quickly. It looks stupid. It looks really silly. I quite enjoy this animation quite a bit. It's kind of just... you're doing that Sonic run where you lean really far forward and your arms are wiggling. This is an animation that is going to be played at maybe 6 times its regular speed. It doesn't have a whole lot of upper body or arm movement. They're sort of just swaying around. This is because it's playing at a very high speed. Essentially, if we have grappled from a point and we've flung ourselves onto the ground and we're still maintaining this speed as we're running and slowing down, we're going to be playing this running animation. Or if we're running towards a tight, tense rope, we're going to be building speed like this and running like this. But the reason I'm showing off this animation is mostly to talk about some weird power creep that is occurring with these movement systems. If you're unfamiliar with power creep, it is a thing that happens in video games or card games where, as it goes on, new things that are introduced are more and more powerful than the original things in the game. But my power creep is... everything is going faster than it was originally designed for. For example, the base speed is around 7, and the maximum speed of grappling hooks is around 30, 35. It's a lot faster than the base running speed. This has sort of happened over time where I've implemented new movement systems on new equipment mechanics, and they're gradually getting faster and faster, and I just like going quick. I like going very fast. I don't think this is particularly an issue because a lot of the new movement mechanics I want to add, they're more mobility based in opposed to speed based. So I think, for example, the tension ropes that we are looking at now, they're still very speed based and you can go very quickly with them, but they're more mobility based in how they move about. They're more for maneuverability and opposed to just going very quickly. I would say the skateboard is sort of like that as well, where you can go very quickly, but it's tricky to do, and then the sliding is for building speed and going down slopes. The point of this is that every new thing I add is getting exponentially faster than the previous movement thing I have added, and I think eventually I'm just going to have to rework all of the movement speed values so it's a bit more balanced. Next we have how the grappling hooks work in air. This is very similar to the way they work on the ground. They have a similar building of speed. The speed that they build is not influenced as much as the ground speed building, and they have different state transitions, but essentially using our grappling hooks in midair is the same as using them on the ground, with a few minor alterations. The first being that gravity is affecting us as we are grappling hook in the air. This is affecting our Y value, meaning as we are grappling hooking, we will slowly be pulled down by whatever our gravity amount is in midair. So if we are trying to go upwards with our gravity velocity, eventually we're going to be starting to be pulled downwards, but since we're attached to grappling hook ropes, the gravity influence is not as much because we are still tied by things that are tethering us and making sure that we aren't just falling down as we would normally be if we were in mid-air. So the first thing that is the difference is the gravity is calculated when using our grappling hooks in mid-air. The next issue that I had to accommodate for is the amount of control the player has when using grappling hooks in midair. With the current setup, the player has very minimal control when moving in midair, and that's not a huge desirable thing. I do want the player to actually be able to control how they are moving in midair, even if they are being pulled along by grappling hooks. So what I added is the strafe function. This is a function that makes it so the player has a lot more control in their movement patterns when in midair, when pressing directions away from what the grappling hook's direction is. Essentially, if we are having a grappling hook pulled from the left and we are pressing right, this will implement the fact that we are being strafed towards the right. This scripting will detect that we are trying to strafe, and we will add more of a dependency to move in the right input direction when using this strafe function. However, as we are using our strafe function and we're trying to pull away from our grappling hook position points, this ability, air quote, it's not really an ability, this function of movement is being drained, so the longer we try to strafe away from our grappling hook inputs, the more we are going to be pulled towards them. This is sort of a system for you going around tight corners, perhaps, where we don't want to be pulled directly towards where we've hit a grappling hook on the wall, but we want to be pulled slightly towards it and then curve around a wall, for example. I don't really know how to describe this. It's a very complicated thing to describe audibly. What we want is the player to have a bit more control when using their grappling hook, but not to have complete control to just ignore the fact that they are using their grappling hooks and default to input directions. I also may debate adding a function in the future where the player can also boost very quickly using input directions when grappling hooking in midair. This is adding a different variety of strafing. Essentially, if you are holding an input in midair while using the grappling hook and then release your input and then press an input again, we will be boosted in that direction for a small amount. I just got the idea for that off the Attack on Titan fan game. That's very good. I don't know how much this would work for my game, but it's a good idea. Who's to say? And that's pretty much a covering of everything I did this week in terms of implementing the rope system. As you can probably tell, this isn't finished yet. Next week will be further polishing of this system, really working out those details. In fact, the point at which I am recording this audio, I have not even been able to test the current rope physics in the game. So here's hoping they actually work. And I'm not just sounding like a fool on top of a broken game system that is being played. I hope I only sound like a fool for the regular reasons. There's a lot more complexity I want to add to this completely optional equipment item, so I will be excited to delve into that next week and add more detailing to this system. I wonder how this system will work with the eventual adding of combat. Will there be attack strings for when you are using your grappling hook? Probably. Who knows? It's a mystery. If you liked the video, like and subscribe. If you have any suggestions or you would like to comment, thanks for watching. Question mark? I enjoyed making this system. I don't remember if I mentioned that earlier in the outro section. This was a fun system to make. I had fun making this system. It was a whole lot of accounting for how the velocity of the ropes would work in the movement system, but other than that, it was adding a whole lot of unique overrides and movement options based on the rope systems that we have already implemented. It's pretty fun. I have absolutely no idea what this game is going to be or how rope implementation is going to accommodate or make this game fun, but I like it as an option. I've always been pretty fascinated with this whole grappling hook idea. I may just reduce this to one grappling hook, like a actual useful grappling hook, or I may keep it at 2, or I may add 4 or 5. Who's to say what the future holds? Goodbye for real this time. Devlog finished.